Hello everyone, welcome to Protrainy's workshop on Aero Engines. I am Arsha, your host for today's session. Let me give you a brief introduction about who we are. Protrainy is an NSREL IIM Bangalore pre-incubate edtech startup. We are registered with Startup India, Startup Odisha, and OCF. Landing skill requisites which precisely fit market demand is tougher than landing a job itself. That's where we come into play. We prepare engineering students to be industry ready by training them for the essentials required in the field. We believe that skill building is an extensive process which requires detailed and practical knowledge. With the help of our experienced experts, our only aim is to build a skilled workforce for the civil engineering students and to create thought leaders of tomorrow. Protrainy brings to you an involving industry-ready environment to tackle ever shifting business scenario. As an educational platform creator, we upskill civil engineers in technical domain as per current industry trend. From theoretical concepts like structural engineering, bridge engineering to software trainings like Oracle, Primavera, ETABS, AutoCAD, we offer 360-degree holistic development required for civil engineers to become a skilled industry professions. We recently conducted an industry-ready long course on tendering, billing, Primavera, highway engineering, etc. And a good results in these sessions has motivated us to go beyond our boundaries and get more for all of you. To be updated with the upcoming amazing courses, go and follow our Instagram, Facebook, and LinkedIn profile by the name Protrainy. Now I would like to introduce our expert, Arvind Patel sir, who have joined our forces to make everyone industry ready. I would now like to request sir to start this session. Hope you have a wonderful session. Thank you. Sir, now you can start the session.
Yep. Am I audible?
Yes, sir, you're audible.
Okay. Let me share my screen first. Are you able to see my screen now? Hello?
Yes, I'll hear.
Yeah, okay. So good evening, everyone. And I would like to, thanks Protrainy for giving me this opportunity to present a workshop on Aero Engines. And yeah, I would also like to thank all of you for joining this session. So first of all, I would like to start by introducing myself. So hello everyone, I am Arvind Patel, and I've done my master's in thermal science and engineering from IIT Bhubaneswar. And from there, I moved into Balkan, India in 2018 as a thermofluid engineer, where I was responsible for the fluid flow and thermal analysis of Rolls-Royce turbofan engines. And I have working knowledge of oil heat management system and fuel system of Rolls-Royce engines. And I have also worked as a thermal engineer, where I was responsible for the overall temperature distribution, evaluation, and determination of overall temperature distribution and displacements of the RR engines. In the year 2021, I moved into Elton, India in Bangalore as a senior engineer in the thermofluid department, where right now I'm responsible for the thermal analysis of the Rolls-Royce engines. And yeah, moving forward toward the presentation, I'll just give you a brief overview of what coming in the later slide. So I'll start with the basic principle of the Aero engine, and then I'll move toward the working of turbojet engines, and then I'll take you through the basic thermodynamic cycle on which an Aero engine works. Then I'll go in brief I'll give you a brief discussion about the components of the Aero engines, like the compressor, a combustor, and the turbine. And then we'll move toward the type of jet engines right now in the industries, like the turbojet engines, turboprop engines, turbofan engines, and what's the difference between the high bypass and low bypass jet engines. Then I'll take you through the testing of Aero engines, and at last I'll give you a brief overview of like how the analysis approaches in an Aero industry. So yeah, let's start it. So let me give you the basic, let's start with the basic principle of Aero Engine. So an Aero Engine basically works on the Newton's third law of motion. Okay, that states that for every action there is an equal and opposite reaction. So what engine does, engine takes a large volume of air, okay, and that air is subjected to compression and in the compressor, and then it is subjected to the process of combustion, and then that air is subjected is transferred to the turbine blades, and then it will move out of that turbine blades while pushing the engine in the forward direction. So that's how your engine moves in the forward direction. And talking about the working of a turbojet engine, so here you can see the different components has fan, compressor, combustor, turbine, and the nozzles, which is placed at the exhaust of the engine. So basically we can divide the engine in two sections, as a cold section and a hot section. Okay, so cold section comprises of the processes like suction of the air at the intake, and then that air is compressed in the compression, basically an actual compressor, okay, which increases the pressure of the air. Okay, so this high pressure air is then transferred to the combustor, okay, which is in the hot section of the engine. So hot section basically comprises of the combustor and turbine and exhaust, okay, in which we'll have the process of combustion, expansion, and exhaust. Okay, so in combustor, the high pressure air is mixed with the fuel and it's ignited. So when the ignition takes place, because of the combustion, the internal energy of air increases, which increases its velocity. So that high velocity air is then transferred to the turbine, and from turbine it transferred to the atmosphere through exhaust, which applies a force towards the engine in forward direction, and that's why your engine moves in forward direction. So that's just a brief working of a turbojet engine. Talking about the thermodynamic cycle, so an Aero engine basically works on the thermodynamic cycle, which is known as Breton cycle. So Breton cycle basically comprises of 4 different processes, like the isentropic compression, constant pressure heat addition, isentropic expansion, and constant pressure heat rejection. So if you consider the air which is at point A, okay, so this air point A represents the atmospheric pressure here. So air is compressed in the compressor, okay, which is an isentropic compression process. But in practice, there is no isentropic compression process takes place because of the losses that we encounter in the compressor. So A to B represents the compression process. Then at B to C in combustor, we will mix the air with the fuel and we ignite it. So the process of combustion takes place at almost a constant pressure. So that's represented by B to C. And from C to D, that high velocity air, high temperature air is then transferred to the turbine blades, where expansion of air takes place. So this high velocity air then comes out of the engine through exhaust, and which releasing the heat to the atmosphere, which is represented by the constant pressure heat rejection process. So that's basically the thermodynamic cycle of an Aero engine, which is known as the Breton cycle. And moving forward, there are certain parameters like pressure, velocity, and temperatures. So what happened to those parameters when air enters the engine and it moves out of the engine? So when air enters the engine during compression, okay, the compression during the compression process, the pressure of the air increases. Okay, and so that high pressure air is then transferred to the combustor, where combustion process will increase its internal energy, and directly it going to affect the velocity of the air, and this high velocity air is then transferred to the turbine for expansion. So how this this conversion of pressure, velocity, and temperatures takes place? So this takes place due to the effect of the shape of the engine. Okay, so that shape is created in such a way that during compression, as you can see, in compressors, the height of the blade keeps on decreasing. Okay, so as the height of the blade keeps on decreasing, a divergent cross section is created here. So when air passes through the divergent cross section, okay, it will going to convert its kinetic energy into pressure energy. So when you will have the kinetic energy here at the inlet, and when it moves through the divergent cross section in the compressor, will have the what you call high pressure energy. So this high pressure air is then entered the combustor and it mixes with fuel, as I told you. So during the process of combustion, okay, this high the internal energy of that air increases and it moves toward the turbine. So as you can see in turbine, the height of the turbine blades keeps on increasing as the stages increases. The height of turbine blades keeps on increasing. So we'll have a converging section here. Okay, so because of that convergent passage, that energy, that what we call the combustion energy that possessed by the air, it gets converted into kinetic energy. So we'll get high velocity of air at exhaust. Now, why I'm focusing on high velocity of air at exhaust, because of the formula of thrust, you know that change of momentum is directly proportional to the mass flow rate, as well as it's basically a product of mass flow rate and the difference in velocities. So if you consider the inlet velocity as vi and the outlet velocity is v naught, okay, and mass flow rate is m, then the product, that m multiplied by the difference of the velocity, will give you the thrust that going to be act on the engine. So if your change in velocity, yeah, okay, is more, then the thrust that is acting on the engine will be more. So that's why we want high velocity stream of air coming out of the engine. Talking about the components of the aero engine, so the first component of an aero engine is the fan. Basically, it's made up of titanium blades, and fan itself sucks a huge amount of air into the engine, and the air that sucks into the engine is basically divided into two different components. The first, the half of the air goes into the core of the engine, okay, which will going to be transferred through the compressor, combustor, and turbine, and the rest of the air is going to be transferred through the bypass, okay, which is basically a passage between the core of the engine and your nacelle. So that passage is known as bypass flow. Okay, so bypass flow is nothing, it's just providing the high velocity air just through by passing through that fan. The velocity of, because of the compression, the velocity is also increases. So this high velocity of air is directly passing through that passage, that is called your bypass flow. So that engine is getting thrust through the bypass as well as the air which is coming out of the core of the engine. So that's the basic function of the fan, which is provided at the start of the engine. And not all the engines installed fan. Okay, so we have different types of jet engines based on that. So I'll discuss that in the later slides. Moving to the compressor. Basically, compressor, as you can see, has number of stages. These rows of blades just represents the different stages of the compressors. So basically we'll have 8 stages in a compressor, and it's an axial compressor. So by axial compressor, what I mean, if the flow direction of flow of your fluid is parallel to the axis of the compress, then we'll call it as axial compressor. Okay, so and in aero engines, right now we use axial compressors. We have aero engines that uses centrifugal compressors as well, but in centrifugal compressors, the direction of flow of air will be perpendicular to the direction to the axis of the compressor. Okay, so it has some disadvantages, because that's why we use axial compressor, because we can add stages, as much stages as we want here, and we can get the pressure ratio we want. So in aero engines, we use axial compressors. Most commonly we use axial compressors. So yeah, basically the main function of compressor is to increase the pressure of the air as it passes through the different stages. And after the after the exit of the compressor, the air is passed to the combustor. So as you can see, it's shown as one of the nozzle of the combustor. Here we have 20 different nozzles which sprays the fuel to the compressed air, high pressure compressed air, and we ignite that mixture of air and fuel. So due to the ignition, there is an increase in internal energy of the air. Okay, and we'll get high, it will also going to increase the temperature, as well as it's going to increase the velocity of that air. So that high pressure, high velocity, high temperature air moves from the combustor to turbine. And just for your information, the temperatures reaches up to around 3000 degrees centigrade at the entry of the turbine. So we need the turbines to be made up of titanium alloys, okay, which can withstand high temperatures and they don't melt. And that's what make your aero engines very costly, because the cost of a single blade is very high. So moving to the turbine. So as I mentioned, the product of combustion, that is the air and fuel, after getting ignited in the combustor chamber, it moves with high velocity and with high temperatures to the turbine. Okay, so basically we'll have three different stages of turbine, which can be mentioned as high pressure turbine, intermediate pressure turbine, and then low pressure turbine. So three different stages, your high velocity air will pass through, and the energy that is produced from the turbine is used to run the compressor and fan as well. And at the exit of the turbine, the air enters the nozzle, which is placed at the exhaust of the engine. So basically what nozzle does is it mixes the low temperature air which is coming from the bypass and the high temperature air which is coming from the core of the engine, and it will help in increasing the velocity of the air as well, so that we'll get the more thrust. As I mentioned, thrust is basically a product of mass flow rate and difference in velocities. So nozzle plays the part of increasing the velocity as well. And it has a mixer. Okay, it has a mixer at the end. I'll show you at the end. It has a mixer placed at the end which mixes your bypass air and the air which is coming from the core of the engine. Moving toward the type of the aero engines we have. So first engine is your turbojet engine. Okay, so turbojet engine is basically a simplest form of engine in which we do not have a fan. Okay, we basically have the compressors, combustor, and turbine. Okay, we have the combination of these three, and as you can see on the right side we have an engine with fan, which is not a turbojet engine. It's just for the purpose of comparison I've placed the picture here. So as you can see, we have three fans at the start which are not presented here in turbojet engines. So basically turbojet engines sucks all the air, compresses it, then transfer the air to the combustor, and at last from through turbine it leaves the engine through nozzle. So in turbojet engines we don't have a fan. Then after some time, we got a new design where we installed a fan at the front of the compressor, and that type of engine is known as turbofan engines. So what's the advantage of turbofan engine is that turbofan engines will provide you two different type of thrust. We'll have a bypass thrust because of the bypass air coming flowing in between the passage of the core of the engine and the cover. That cover the cover is known as nacelle. Okay, so the passage between the nacelle and the core of the engine is known as bypass. Okay, so the air that is coming through that bypass is having certain velocity, which is much higher velocity. So this high velocity is going to be move out of the engine through the exhaust only. So it's going to add to your thrust. So that thrust is called bypass thrust or fan thrust. And the rest of the air that is not going through the bypass is going through the core of the engine. Okay, where it will be subjected to the compression, combustion, and then expansion in turbine, and it will leave the engine, adding thrust to the engine. So in turbofan, what is the advantage of turbofan? When we want to have the fuel efficient engine, because for the same amount of fuel, turbofan engine will produce more power as compared to that of your turbojet engines. Or you can also say that for the same supply or for the same amount of power, okay, your turbojet engine will consume more fuel as compared to turbofan engines, because it is also producing the thrust through bypass. So these are the basically two types of engine, turbojet and turbofan. Then there comes turboprop. So turboprop is basically similar to your turbojet engine, which comprises of your compressor, turbine, and exhaust. But the turbine is connected to to a gearbox. Okay, so it's connected to a separate shaft through a gearbox, and that gearbox is connected to a propeller. So propeller is nothing, it's just doing a function of a fan only. It's going to increase the flow of air passing through the passing through your engine. So it's also going to add thrust to it. So that type of engine is called turboprop engine. And based on turboprop engines, we'll have turboshaft engines. Turboshaft engine is similar to a turboprop engine. The basic difference is that instead of having a propeller, the turbine shaft is connected to a gearbox, which is separately connected to a rotor. which is your helicopter rotor. So that's in helicopters we have turboshaft engines, but the working principle is same. That's compression, combustion, and then expansion in your turbine. Moving to another type of engine is ramjet engines. So ramjet engines are basically sort of engines which does not have any moving parts. Basically, it have a variable area at the starting, and because of the shape of the engine, will have a divergent section at the start and convergent section at the start and divergent section after the combustor. So what happens here, when air comes into that convergent section, the speed of that air is lesser than the speed of your sound. That is, the Mach number is less than 1. So for that convergent section will going to increase the your pressure energy, that going to convert the kinetic energy into pressure energy, and that high pressure air then passes through your combustion chamber. That small ring indicates your combustion chamber or combustor. So after moving to that combustor, the divergent section will act as a divergent nozzle, which going to increase the velocity of air passing coming out of your nozzle. So that type of engine is called ramjet engine. So thrust produces through this type of engine is very less, so we use this type of engine in your guided missiles. Okay, so guided missiles basically have ramjet engine. Now coming to the bypass flow, I would like to add more to this. As I mentioned, the fan sucks the air, and that air gets divided into two different portions. The air which goes through the duct between the core of the engine and nacelle, sorry. So that bypass flow, that flow is known as bypass flow. So based on that, we have two different type of engines. So the ratio of the mass of air that is going through that duct, bypass duct, divided by the mass of the air going through that core section is known as bypass ratio. So if the engine can be divided into high bypass engine, okay, and low bypass engine. So as I mentioned, the fan is going to high bypass engine is going to have thrust because of that air as well. So high bypass engine is going to have more fan thrust as compared to your jet thrust. By jet thrust, I mean to say the thrust that is produced by the core of the engine. Okay, so we have two different type of thrust: core jet thrust, which is produces by the core of the engine, and bypass thrust, which is known as the fan thrust. So high bypass engines will going to have more fan thrust when compared to the low bypass engine, which is having the more jet thrust. So as you can see here, the left hand side shows the low bypass engine and right hand side shows the high bypass engine. Now that low bypass engines are basically installed in military aircraft because there we are more focused toward the thrust, as well as the space restrictions are there. So we cannot use high bypass engine there. Okay, and we are not worried about the amount of fuel used in the military aircrafts, whereas in commercial aircrafts we are more worried about the fuel efficient engines. So we installed high bypass engine in commercial aircrafts. As you can see, this is a Pratt and Whitney engine, okay, and which is a low bypass engine. As you can see, there is no fan installed at the front of the engine. And this is a Typhoon engine, which is used in your Typhoon fighter jet. Okay, it's also a low bypass engine. We don't have any fan here. But when you looked into the commercial aircraft engine, this is your Pratt and Whitney PW4000. We have a bigger fan at the front of the engine. Okay, so that's a high bypass engine. Similarly, well, we are having a G90. It powers your Boeing 777, and I think that's the most powerful aircraft engine right now. So at last, I would like to add about the afterburn. So afterburn is nothing. It's just a combustor which is placed at the end of the at the end of your turbine, so that the air which is coming at after the turbine is mixed with the fuel again, and we have one more combustion there. So why we are adding combustion after the expansion to the turbine? Because we want to add more velocity to the flow. Okay, so more velocity, we're going to increase the thrust as well. So we have afterburner. So afterburner is basically nothing. It's just a combustor which is located at the rear of a turbine. As you can see here, we have the turbine here, combustor, then we have turbine. So after turbine, we have a unit which is called afterburner. So afterburner is nothing, it's adding fuel at the end and it's igniting it, so that will have more velocity fluid coming out as an exhaust, which is going to increase the thrust of the engines. We have basically these on your fighter jet planes, as you can see. And we also classify engines based on the arrangements of the shafts. Okay, we have two different types of arrangement, 2 spool engines and 3 spool engines. So by 2 spool engines, what I mean, when your high pressure compressor, your high pressure turbine is, which as shown in red, is connected to your high pressure compressor, and your low pressure turbine is connected to your low pressure compressors through concentric shafts. Okay, these are two different shafts, okay, which connects your turbine to your compressors, like high pressure turbine to high pressure compressor and low pressure turbine to your low pressure compressors. So these type of engines are called 2 spool engines, and basically G Aviation, creates such type of engines. So G produces 2 spool engines. When you talk about 3 spool engines, we have 3 different sections. Like we have your fan, which is your low pressure compressor here. Then we'll move to the orange one. It is your intermediate pressure compressor. The red one is your high pressure compressor. Okay, and if you move toward the right, the red one is your high pressure turbine, then your intermediate pressure turbine, and at last low pressure turbine, as your pressure keeps on decreasing. Okay, so this low pressure turbine is connected through a shaft to your low pressure compressor. Then your intermediate pressure turbine is connected to your intermediate pressure compressor through a orange shaft or through a separate shaft, and your high pressure turbine is connected to a high pressure compressor. So this type of engines are called 3 spool engines, and Rolls-Royce manufactures these type of engines. And yeah, coming to the testing of the engines. So basically a company spend a lot of money for testing the engines. So a company basically tests their engine on ground level conditions, high altitude conditions, and it also tests their engines for the environmental conditions, like if your engine is subjected to hailstorm or rain, or there are situations where a group of birds strikes the engines. So that's called bird strike testing. And there is a type of testing in which your blade of your rotor turbine or compressors moves out, so that it won't affect the airplane, and it only damages your engine. So that type of testing carried out by the company. So first one is your ground level testing. So in ground level testing, we have a test bed, and that in that test bed we'll run the engine with its full capacity, and to evaluate the pressures, temperatures to which all the different components are subjected. Okay, so that type of testing is called ground level engine testing test facility. Then we have altitude test facility, in which we creates the effect of high altitude environment, because as you goes on, keeps on moving in upward direction, the pressure and temperatures changes. So based on that pressure and temperatures, we creates that environmental condition and try to run the engine and estimate like how the engine of behaves at that high altitude conditions. So that test is called altitude test facility. And this is one of the most important test, because the Federal Aviation Administration, that's called FAA, and these are they provides the safety certificate to the jet engines. So they provide they ask to have that type of test, which is called blade of testing, or in Rolls-Royce we called it as fan blade of test, FBO. Okay, so what we does in this type of testing, we just lose one of the blade of your fan, either of your fan, compressor or turbine, and we starts the engine to its full capacity. So as the blade gets loosen at the root of or where it is connected, okay, it gets removed and it damages the engine, and it's very severe. I just wanted to show you a video of that. If you all I just want to show you this. So this is what they are doing. They are testing right now the flame blade of test. So as you can see, the orange or yellow colored blade is there. Okay, so that blade is looser at the base. Okay, so when the engine is running with its full speed, that blade will come off, and it damages only the engine. Okay, it won't come off. Yeah, as you can see, they just destroyed $1 billion engine just for the for our safety. Yeah, this blade. They are testing this blade. So this blade is loosened at its base. This is your bird ingestion testing. So they will just transfer the bird through that engine and check whether it's working fine. Then they have the water ingestion testing, in which they will subject the engine to the environmental conditions like hailstorm, or the cold testing, like when they test the engine at the coldest conditions. This is your water ingestion testing. Yeah, they test the engine in the coldest condition. And yeah, at last I'll take you through the analysis approach that we used in our industries. So basically, your entire engine is first tested for the fluid flow analysis. Okay, in which in this fluid flow analysis, they have their own in-house softwares. Okay, and those softwares are able to use the equations of the fluid flow and heat transfers. So by using those equations and solvers, they can evaluate the pressures and temperatures as well as the flow rate of the airs going through the engines. So that is called the fluid flow analysis of the engine. And based on the output of that fluid flow analysis, okay, they will use the pressure, temperatures, and flow rates obtained from the fluid flow analysis for the thermomechanical analysis. Okay, so thermomechanical analysis is basically a 2D analysis in which we'll use the output from the fluid flow to obtain the metal temperatures, like the temperatures of the blade, hub, as well as the different components in the engines. So metal temperatures are obtained from the thermomechanical analysis. And after obtaining the metal temperatures, we use these temperatures to evaluate the stresses that are induced in different components of the engines. And that's we called as a structural analysis. Okay, so that structural analysis, as you know, temperature subjects affect your stresses as well. If you are aware about the thermal stresses, so thermal stresses induces axial as well as radial stresses in the different component of the engines. So we do that analysis in structural analysis. So that this is the basic analysis approach right now available in the industry. And we also do the CFD analysis of the turbine blade, compressor blades, and different components of the engines to evaluate these CDs, the coefficient of discharge, through CFD analysis, and as well as we also use the CFD analysis to evaluate the coefficient of pressures, okay, which we use in different analysis of the engines. So yeah, I think that's all from my side. So if you have any questions, please feel free to ask. I think that's all from my side.
Thank you so much, sir, for such a lovely session. And dear learners, I have just shared the link in the chat box. Kindly fill that so that we can generate like certificate of yours. Thank you. And if you have any doubts, kindly ask to the expert right now.
ये मैम पीपीटी मिल सकती है?
Yeah, for sure. I'll send the PPT to anyone, like one of the say Ayush or someone, and then I think you'll get from them. I'll send the PPT to Protrainy.
So yeah, okay. I think there's no doubt, sir. We can wind up the session now. Thank you everyone for joining it.
Okay, thanks. Thank you, everyone.